Hey guys, Mr. Kaneko here. We're introducing thermal energy and heat today. You are going to watch this video and then you're going to answer the questions on investigation one. So, real quick, make sure that you are on lesson 10, uh, investigation notebook. And then you're going to click this arrow for investigation one. When it is time to answer the questions, you're not going to answer question one. You're only going to answer question two, three, four, and five, and six. Okay. So take a look over here. All right. So we're going to identify thermal relationships. Right? Understanding thermal energy and heat requires us to understand kinetic and potential energy. Remember, kinetic energy is our energy of motion. Potential energy is our stored energy. Right? Remember, for your roller coaster, potential energy would have been the top of your roller coaster before you drop that marble. Bottom of the roller coaster, kinetic energy wouldn't be moving throughout. And top and bottom of any hills, you may have some potential energy as well. Okay, so we can understand how these terms are related with an example. Suppose your grandfather is cooking a marinara sauce on the stove, like a red spaghetti sauce. Before he turns on the stove, he places the thermometer in the sauce and it reads 50 degrees Fahrenheit. So what does that thermometer measure? Okay, well, the thermometer is going to measure the temperature of the marinara sauce. So temperature is the average kinetic energy of particles in the sauce. Remember, kinetic energy is moving particles. So the thermometer detects how many particles are moving around. Either they're vibrating slowly or they're colliding into each other and bouncing off each other. Okay? What do we think is going to happen when the grandfather turns on the stove? Right? Well, the heat from the stove is going to warm the pan in the pot, which is going to increase the temperature of the liquid inside that pan. In this case, it's our marinara sauce. Heat is thermal energy that is transferred, okay, from one object to another. When heat flows from the stove to the pot, the thermal energy of the pot increases. The heat causes an increase of the kinetic energy of the particles in the pot. So when we heat up the pot and the particles start moving faster and faster and hitting each other more, moving faster and faster. Okay, it is then transferred to the sauce. These particles in the sauce also experience an increase in average kinetic energy. So again, the particles in the sauce as well are moving fast. Okay, the sauce gets so hot that it starts to boil. This means some of its liquid begins to change from liquid to gas. During the change of state, the temperature does not change, but the heat is still being added to the sauce. How is this possible? Okay, well, some of the heat is absorbed and goes into breaking the bonds between the particles. Okay, so for instance, when you're boiling water, you have H2O, two hydrogen, one oxygen. Okay, so you heat it up to get those particles moving. Some of that heat then in turn is used as heat energy to break apart the hydrogen from the oxygen, evaporating the water, turning it from a liquid to a gas. But remember, temperature only measures the average kinetic energy of the particles. The energy that is absorbed during the change of state affects the bonds between the particles, but it does not change the kinetic energy of the particles. Therefore, the temperature does not. When the sauce is done cooking, your grandfather allows it to cool on the stove. The heat transfers to the air. The sauce will cool until it's the same temperature as its surrounding, room temperature. What is it called when two regions are the same temperature? So, for instance, if the sauce and the air around it are the same temperature, we would call that thermal equilibrium. I mean, equilibrium meaning the same. Cold doesn't flow. Cold is just the absence of heat. So when something cools, heat is flowing away from it. So it's losing heat. Okay? You can think of heat and coldness like dirt and cleanliness. Heat is like dirt, it can move from objects or it be removed from objects. But cold, like cleanliness, is the result after the heat moves. Okay? So if we have arrows that we draw here, we would show arrows of the heat flow as the sauce cools. Okay, so if we drew arrows here, we would have the heat is leaving the sauce and going into the air around it until they are the same temperature. Okay, what we're going to find out is that it goes from hot to cold. The heat is moving. Okay, nothing is going into the sauce, all the heat is leaving the sauce. So again, we get the same temperature or thermal equilibrium. Now it's your turn. Okay. The heat in hotter regions spreads to colder regions. As a rule, energy always flows from hot to cold, not the other way around. Everything goes from hot to cold. So now in your notebook over here, you are going to draw the arrows to show the direction of the heat flows in each of the images. So I want you to pause this video. Okay, get over here and you're going to answer question 2. You're going to draw your picture. Question 3, you're going to draw your picture. Question 4, you're going to draw arrows showing how the heat flows. By now, you should have unpaused your video after you didn't check your answers. Okay. So again, the heat is leaving the polar bears into the cold air and onto the cold ice. Remember, we always go from hot to cold. We don't go from cold to hot. Okay, here we have a cup of coffee, and we're going to assume that the coffee is hotter than the air around it. So again, the heat is leaving the cup and the coffee and going into the air around it. And lastly, we have a glass of iced tea here. Okay, and notice that we have ice cubes inside there. So the ice cubes keeping it cool. So the heat from the outside of the glass is going into it, and which is essentially is going to cause the ice cubes to melt. All right, back here real quick. All right. So you should also be answering questions 5 and 6. Okay, in all of the images, when does the heat stop flowing in each system? Remember, heat stops flowing when we have a thermal equilibrium, right? When they're both the same temperature on the inside as they are the outside. Okay, and 6, when the objects reach thermal equilibrium, what does that say about the temperature? I just answered that a little bit, but they're going to be the same temperature. They're going to have equal temperature. So we're going to skip this part. Just think of some follow-up questions. How could you warm something up? How could you cool something down? And how does heat flow in each example? As always, ask us if you have any questions. We're done here for today.